record. All right. So this is unit 3. This is the populations. So we're going to go over a couple of definitions of different kinds of species, R and K, and then we're going to end looking at human population. So first thing, generalist versus specialist. By the end, you should be able to identify the differences. And in order to do that, we're going to define them. We're going to go over some examples and look at the facts that specialists will have advantages in habitats that are constant with no change. Generalists have the advantage in changing habitats. So in general, a specialist has a narrow niche, less adaptable, uses specific resources, more likely to become extinct, easily affected by change, and has an advantage when conditions are constant. Generalists, basically the exact opposite. So specialists would be things like the panda or the koala. They each eat one type of plant. Generalists are things like raccoons, which eat anything. If you've ever seen one going through a trash can, you know that. Mice, another good example. Generalists, variety of niches, can avoid predation because they can move to other areas and eat other things. So they tend to be able to withstand environmental change easier. If we're talking about plants, they don't have soil requirements. Like their soil requirements are basically that there is soil and can live basically anywhere. Specialists, again, one niche. Animals might eat just the one thing. They may not be able to migrate if conditions change because they rely on that one type of food. Plants would have strong soil requirements. A good example of plants would be like the Venus flytrap, which really only grows well in areas with acidic soil. Now we're going to talk about K versus R selected, and we're going to see that this is kind of related to generalists versus specialists. So we're going to go over basics of each, discuss biotic potential, discuss species that are in between the R and the K, and discuss how invasive species impact both of them when introduced, and make sure we mention that invasive species, most of them are R selected. All right, so R versus K selection. R selection tends to do better in variable climate, unpredictable climates, because they can adapt or move. K selection need those constant things. We're going to talk, we'll kind of skip this mortality issue until later. Population sizes of R selected are variable, well below carrying capacity typically. K selection, they're constant and tend to be at carrying capacity. That's where we get the K from, is from carrying capacity. R selection, they have large juvenile mortality. They have multiple batches of kids each year with many, many children at once, and they don't take care of them. In K-selected species, we tend to have either constant mortality or large adult mortality, and these things have just 1 or 2 babies only once a year, usually. So they're gonna have lots of parental care. So our selection species will have early reproduction, so they become mature earlier, tend to be small in body size, and don't worry about this one, this is not on apes, but it was in the diagram I found that had all the other stuff we need. K-selected species have delayed reproduction, so they don't become mature until later in life and tend to be larger in body sizes. So just some of the key things again: K-selected, large, few offspring per reproductive event, stable environments, spend energy on the offspring so they have that parental care. Competition for resources in their habitat is usually high. So they're usually right around carrying capacity and competing for resources. R selected, small, have lots of offspring, don't put a lot of energy into their offspring, mature early, have lots of babies many, many times, or they reproduce only once in their lifetime. There are 2 kind of ways to do this. Sea turtles will reproduce every year, but tend to go on this R selected where they have many babies at once and most of them die. Whereas some other species will have babies and that's it. They have 1 batch of reproduction and then they die. Typically for R selected, competition for resources is relatively low. There's usually plenty of resources for all of those offspring that will survive. Now, not everything is definitely K or definitely R. So for example, turtles, they're large, but they lay tons of eggs at once and hope that they live. They also reproduce like every year instead of only once in their lifetime. Coyotes are K-selected reproductively. but they're generalists and good at going into new habitats, which is typically an R-selected species trait, because R-selected species usually take advantage of new opportunities in like habitat and resources. So those are two examples of things that are kind of in between R and K. Biotic potential is the maximum reproductive rate of a population in ideal conditions. So basically it is the rate of reproduction plus the size of the litter. So rate of reproduction would be how often they reproduce. So for, you know, rabbits, it might be like 5 times a year. For elephants, it might be 1 time every 2 years. So it's going to change depending on the species. And then the size of the litter, so for bunnies, I don't know, that might be 8, and for elephants, it might be 1 to 2. Those are going to be key factors in telling us how many babies they could have quickly. Typically, R-selected species have a higher biotic potential, or what we call fecundity, than a K-selected species. And of course, this is not just a like black and white thing. There's a lot of gray area between R and K, where bunnies, like in this example that I gave here, the 5 times per year, which I'm just making up. They might be more or less than that, but they would be somewhere in between. They tend to have litters much more frequently than things like elephants. Invasive species tend to be R-selected. They multiply quickly. They are generalists, so they tend to fall into this R-selected pattern. And then, of course, the invasive species will tend to impact K-selected species more than R-selected species. And that's because if an invasive species moves into a habitat, it can destroy a K-selected species, which then won't be able to reproduce fast enough to replace whatever animals are killed by the invasive. Whereas if it moves into an area and there's lots of R-selected species, the other R-selected species usually can continue to reproduce quickly. This is why you see like kudzu usually has more of an impact on trees than it does on like wildflowers. Things like wildflowers are still going to be reproducing at a pretty high rate, even when you have kudzu also on the ground. All right, next is survivorship curves. This is our type 1, type 2, and type 3. So we'll also relate this to our R and K. So here we have our type 1 curve, low infant mortality. Mortality happens later in the life cycle, so that would be humans. This is usually a K-selected trait. Type 2 is usually somewhere in between, so birds would be a good example. Have some mortality as eggs, and like mortality throughout the lifespan is about constant. And then here we would have an R-selected, type 3, where we have lots and lots of acorns, but most of them don't grow into trees. And then once they grow into a tree, they live a very, very long life. Most of them will die before they even sprout from an acorn, or when they are tiny little oak sprouts. So type 3 tends to be R-selected, lots of babies, don't care after them, many die shortly after birth or hatching. Type 1 tend to be K, few babies, lots of care when young, live to adulthood, and then die in older age. All right, carrying capacity. We're just going to define this because all you need to do for this section, according to College Board, is describe carrying capacity and describe the impact of it on ecosystems. So we're going to define it and discuss what happens after we overshoot the carrying capacity. So here is carrying capacity, resources available for growth, limits to X number of individuals. So in exponential growth, there's no limit. In logistic growth, we have the carrying capacity. We are limiting our population size to whatever this number would be. So say it's 20. When our population hits about 20, it should level off. Now, it's not going to immediately level off because animals don't talk about that stuff, or plants. So it's going to kind of do this kind of thing around that carrying capacity number, which is on this graph here. So K-selected species, the term comes from K for carrying capacity. And so a species that is really K-selected will like go around that carrying capacity just a little bit, just a few more species, a few less species. Because they have small litters, you're not going to see huge changes in population size. An R-selected species, you might have a lot of variation around the carrying capacity, because what happens is they go through exponential growth until there's way too many animals because they have babies so many babies at once, and then the population will crash. And then again and again and again. Now, this is a very simplistic view. This R and K hypothesis is kind of not used in a lot of ways anymore because it gives us a good way to like differentiate species that have R characteristics or K characteristics, but it doesn't tell us like anything real about like how these species are definitely going to act, because there's a lot of in between. There's a lot of species that are in between R and K. All right. So population growth and then resource availability. So we've already talked about carrying capacity, and that's related to our resources that are available. So we're going to talk about how resource availability affects population growth, and then just kind of go over population growth. So we'll talk about limiting factors. We'll discuss what happens when resources are abundant and when not available. So limiting factors. There is a limit to them, and organisms need them, basically. So these are anything that could limit our population size and be part of our carrying capacity, like limit. Food, water, space, availability of light, lots of things. When we have plenty of those limiting factors, we would have exponential growth. When we have limits on what is available, that's when we hit carrying capacity and have logistic growth. And this seems to be more important than that R and K selection for most animals. Now there's going to be some where we have like species that will exhibit very strong R characteristics or very strong K characteristics, but in the things that are in between, the limiting factors available to like ducks, for instance, are going to be much, much more important in population growth than whether we would consider ducks R or K selected. This is where we come into density dependent versus independent factors and how they impact carrying capacity. So a density dependent factor has an effect based on the number of individuals. We know about this for disease. The whole world is learning about it right now as we go through this whole COVID-19 like stuff and we stay home, right? Because we are trying to decrease our density because disease transmission is density dependent. This is why we see many, many more cases of COVID-19 in the bigger cities like New York than we do in small towns. These aren't a factor usually unless you are near carrying capacity. Density independent factors, these have an effect not based on the number of individuals. These are like disasters. They affect everyone the same no matter how many you have. So forest fire, flood, earthquake, hurricane, they're a factor regardless of the size of the population. So here we have kind of an example of our two growth curves, our logistic and our exponential. So in our exponential, we grow, we grow, we grow. At some point, we've completely run out of resources and the population crashes. This is what happens to a lot of like pests. You might see this happen with like termites eating an old log, like their population will increase, increase, increase until there's no more wood, and then they will just completely crash. This S-shaped or logistic growth curve, this is where we kind of go around the carrying capacity. And this is going to be related to the fact that these animals, the animals that are K-selected, the animals that would exhibit this type of growth pattern have a longer lifespan than something like a termite or a bacteria, which has a very short lifespan. All right, now we're going to look at the age structure diagrams or the population pyramid. So we're going to go over how to interpret and then how you tell growth rate. And I think most of you guys, I'm hoping, remember this. So this is our age structure diagram. We read it by looking at our age group and whether we're looking at males or females. So if I asked you how many males between 55 and 59, we would look at this bar. We would kind of go down, and that's maybe 11 million. Men between 55 and 59 lived in the US in 2018. Same thing we could do. There were about 10 million females between the ages of 0 and 4. So that's how you read it. Hopefully you guys remember that. We can look at the shape to tell what's happening to a population. When we have many, many more young people in the bottom, that's the pre-reproductive. So this is pre-reproductive, reproductive, and then post-reproductive at the top. If you have many more pre-reproductive than reproductive, you tend to have a growing population. Over here, New Zealand would be a stable population. And you'll notice that the top bar is only so wide because it's 75 and up. So in reality, the shape would kind of continue getting narrower as people kind of get old and die of old age. Over here, again, we have New Zealand to kind of compare to because it's a stable population where we have about the same numbers at the bottom going up to the reproductive age, compared to Japan, which has much fewer children than in these reproductive age categories. And that means that that population is shrinking or decreasing. So rapidly growing equals more young people, declining equals more old people, few young people. So we can figure out population growth rate by putting in like birth and immigration minus death plus immigration. Again, it looks like you're not going to have to calculate, but you should still understand it so you could interpret if they give you the population growth rate information. So this tells us how quickly a population is increasing. Basically, we only divide by 10 because we're using the crude birth rate, crude death rate, crude immigration rate, crude immigration rate. If it is negative, our population is shrinking. If we have a positive number, it's growing. If it's 0, our population is exactly stable. All right, so we can look at charts over time and watch countries kind of go through demographic transition. So here we have our, rapid growth, and then eventually we end up getting to slow growth, usually as countries become more developed, and then to 0 growth, and then possibly to negative growth, depending on what happens in the country. A lot of the countries that have been developed the longest, like went through their industrialization process first, seem to be going into this negative growth phase. All right, we're going to talk about fertility rates now and how that affects growth. If fertility rate is at replacement levels, the population will be stable, and we'll kind of define that. And then we're going to go over infant mortality and how that's going to connect to our overall population growth, because if you're just looking at the number of babies born, but you're not taking into account infant mortality, you might get an incorrect picture. All right, so total fertility rate. What is going to impact it? Well, first, the age at which a woman has her first child. In areas where women start having babies in their teens, they tend to have more babies over the course of their lifetime. Education of women. If women are educated, they tend to delay that age at first child. Also, access to family planning, access to birth control allows them to choose when they want to have babies. And then government acts and policies like the one-child policy can change total fertility rate. So our total fertility rate is the average number of babies a woman in an area would have in her lifetime. So worldwide in 1900, it was 5. Worldwide now, it is about 2.4. So we have seen a worldwide decrease in the total fertility rate. Currently, the US is 1.8 and Ethiopia is 3.7, just to use an example country with a increasing population pyramid, since that's the one I showed you on a couple slides ago. Replacement level fertility, ideally it would be 2. It's a bit higher due to infant mortality, and I meant this to be Ethiopia. I switched halfway through and used Ethiopia instead of Uganda because I could get better information, more current information like 2017 instead of the Uganda stuff I think was 2010. So therefore, based on these numbers, US is stable, Ethiopia is increasing. Number of deaths of children under 1 year of age per 1,000 births is our infant mortality. And infant mortality is related to a lot of the same stuff that we saw the total fertility is going to be related to. Number 1 of those is education of women. Also, a lot of these nutrition and health things, access to clean water, nutrition, sanitation, those are all going to affect our infant mortality rate, and then prenatal care. And prenatal care is usually related to that age at first childbirth. Women who have their children later in life tend to have access to better prenatal care. So our infant mortality rate, in the US it's 5, in Ethiopia it's 39, and in Japan it's 2. Developed countries usually have lower, and remember this is per 1,000 live births. So per 1,000, and we say live births because that gets rid of people who have stillbirths or miscarriages. Developed countries usually have lower infant mortality because they have better and or easier access to healthcare, they have clean water, things like that. One of the main things that clean water is a problem for is when babies need to drink formula, maybe because a woman cannot breastfeed. In countries without access to clean water, babies might get formula mixed with water that has pathogens in it and then get sick. And they can get diarrheal diseases, which can cause infant mortality. Now, the other thing that I thought was interesting, we talked about this in class, is that infant mortality rates in the US vary by state and by population. So this map is from the CDC in 2017, and it is showing us different states. Southern states tend to have higher infant mortality rates. Part of that is because southern states tend to have looser restrictions on giving birth at home and basically untrained midwives delivering babies instead of only nurse midwives delivering babies. We also see higher infant mortality rates and higher maternal mortality rates among populations of color in the US. And part of this goes into some inherent systemic racism in medicine, which we talked about in class, but you don't necessarily need to know about that for the AP exam. Just a good idea that, like, when I say Ethiopia or the US, our rates are going to be different in different parts of the US, just like they're going to be different in different parts of Ethiopia. All right, so human population dynamics. In this section of the unit, you're supposed to be able to explain how human populations experience growth and decline. We are going to go over what impacts population growth, go over what limits growth. This is the Malthusian theory, Malthus. We talked about him way back in the day, just very briefly. Density independent versus density dependent factors on human populations, and then rule of 70. All right, so you should know these numbers. US population is about 330 million. World population is 7.6 billion currently. That's pretty close to just 7 billion. If you want to say 7 billion or 8 billion, I don't think you get points off for that. China and India are at the top, and they are both close. They are both 1.3 billion. Currently, China is like 1.36 billion, and India is like 1.34 billion. Because of their growth rates, though, India will probably overtake China relatively soon. All right, this is our overall size of the world population growth. So remember that, you know, we have this dramatic increase happening because of industrialization, basically, because of the ability to farm more easily and have people live in cities and bring food to them. We start to see this dramatic increase in population size. And the reason we see it happening between, you know, about 1928 and current is because we have the ability to feed all these people, but we haven't slowed down birth rates yet. Right now, we're starting to slow down birth rates. So we're starting to see this angle, the slope of increase kind of level off. All right, so to go back to Malthus, he was the one who said population growth is exponential, food production is linear. Therefore, there is a carrying capacity for people, and people are going to starve to death when we hit it. Now, when we talked about this, we were talking about it in relation to the Green Revolution. Technology has already let us grow past several points where we thought this might happen because food production capacity jumped. It was no longer linear. And the best example of that is the Green Revolution, which we'll go over again in the agriculture review. So technology has allowed us to kind of not have this dire prediction that Malthus suggested happen. So what impacts the overall growth? This is just a summary of everything we've talked about so far. So birth and death rates, obviously, infant mortality, access to family planning, access to good nutrition, access to education for women. And the reason we say for women is because in most countries it is available to men, at least to some extent, but in many countries it is not available to women at all. And also postponement of marriage and postponement of age at first childbirth. Those are the things that can impact overall growth. So age of marriage or age of childbirth would, if it's young, high growth; if it's older, lower growth. We also have local growth being impacted the same way. So when I say local growth, I mean like the population growth of Florida or the population growth of Somalia or something like that. Now, there are other things. First off, with humans, there's things like war or famine. Now, famine would be one of these density-dependent factors, food and water availability, also disease. Areas that experience, like right now, for instance, Italy is experiencing a lot of deaths of older people from COVID because they have an older population. So they're going to see a different population growth number this year than they would have last year, just because of how many elderly people are being affected. And then density independent factors, these are things like drought, hurricanes, fires, the same things they would be for animals. It could also include things though like war. Typically that's not going to worry about density. All people are going to be negatively impacted by something like that. And last thing for 3.8 is rule of 70. So doubling time equals 70 divided by the percent growth. Again, I don't think you're going to have to calculate this based on what I've read from College Board. But just so that you understand it, if Ethiopia's growth is 2.6% and US's growth is 0.6%, we take 70 divided by 2.6, we get 26.9 years. That is our doubling time. It would be 26 years or 27 years until Ethiopia doubled. Same thing, 70 divided by 0.6 would equal 116.7. And so that would be our doubling time. It would take 116.7 years before the US population doubled. All right, last section, demographic transition. So we're going to go over the graph and compare developing countries to developed countries. College Board requires only these 4 stages. You might see lots of other graphs that include the 5th stage. Don't worry about it. So we have pre-industrial, low population size, high birth rate, high death rate. Transitional. This is where we first see death rate decrease, and then we start to see birth rate maybe begin to decrease at the end of that transitional phase. So this would be decreasing death rate. And birth rate is still high. In stage 3, this is where we start to see the birth rate decreasing. And by the time we get to stage 4, post-industrial, we should have stable, low birth and death rate. And at this point, we may even see the birth rate go lower than we would expect, and our population start to decrease, fall below the death rates. And that is where we would see like stage 5 is usually popped in there. But again, College Board doesn't have that stage 5. I grabbed this one, even though it has 5, because I liked how we could compare it to the age structure diagrams. So our pre-industrial is growing quickly, or has this kind of population pyramid. It's not necessarily growing as quickly though, because we have such a high death rate. Here we have a very rapid increase. Sorry, I misspoke on that one. So for our stage 2, where we have a lower death rate and a still high birth rate, our transitional stage, we're going to have that population pyramid be more like triangular shaped and have a very high increase. By the time we get to stage 3, we start to see the birth rate fall. We're still increasing, but the increase is going to slow down as we start to see the like walls of the pyramid kind of flatten out. In stage 4, we have a low birth rate and a low death rate, and we tend to have a falling growth rate. So that means that our population is still increasing, but increasing slowly. And then here, we would either have stable population or slow increase or even decrease, depending on what happens to the birth rate. Some graphs have the birth rate go back up, some graphs have the birth rate go down. So depending on what happens there, you might have the US kind of pyramid or a pyramid that looks more like Japan. So developing countries, less income, less industrialized, higher total fertility rate, higher infant mortality, high number of children in the workforce, high population growth, low nutrition, sanitation, clean water access, education, and access to healthcare. Developed countries have the opposite. More income, more industrialization, higher levels of nutrition, sanitation, access to healthcare, access to clean water, education, and then low numbers of children in the workforce, lower total fertility, lower infant mortality, and lower population growth. All right, that's it. So we're gonna go ahead and stop the recording.